Try to imagine a vast, flexible sheet. This sheet is not just any ordinary fabric, it is the very essence of our universe, known as space-time. Picture it stretching out infinitely in all directions, a cosmic canvas upon which the entire universe is painted. This sheet represents space-time, the very fabric of our universe. It's an intricate and dynamic entity, constantly in motion, constantly evolving. Every star, every planet, every particle is a part of this grand tapestry. This fabric is not just a backdrop, it's an active player in the cosmic drama. It bends, twists, and warps in response to the presence of mass and energy. It's a living, breathing entity that shapes the destiny of everything within it. Objects with mass, like stars and planets, create curves in this fabric. These curves are not just minor indentations, they are profound distortions that can stretch across light years. The more massive the object, the deeper and more extensive the curve. These curves are what we experience as gravity. Gravity is not a force pulling objects together, but rather the result of objects following the curved paths laid out by the warped space-time. Think of it like placing a bowling ball on a trampoline. The trampoline sags under the weight of the ball, creating a dip. The ball creates a dip, distorting the trampoline's surface. Smaller objects placed near the ball will naturally roll towards it, following the curved path created by the dip. Similarly, massive objects distort space-time. This distortion is not just a visual effect, it has real, measurable consequences on the movement of objects and the flow of time. This distortion affects not only how objects move through space, but also how time itself flows. Time can speed up or slow down depending on the curvature of space-time, leading to phenomena such as time dilation near massive objects like black holes. Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. Einstein proposed that gravity is not a force acting at a distance. Instead, it's a consequence of the curvature of space-time. The more massive an object, the greater the curvature it creates. This curvature influences everything around it, including light. Even light, which travels at the fastest speed in the universe, follows a curved path in the presence of gravity. Black holes provide the most extreme examples of time dilation. These cosmic monsters are regions of space-time where gravity is so intense that nothing, not even light, can escape. As you approach a black hole, time slows down dramatically relative to an observer farther away. If you were to observe a spaceship falling into a black hole, you would see its clock ticking slower and slower. From the spaceship's perspective, however, time would appear to flow normally. This discrepancy highlights the relative nature of time. You don't need a black hole to experience time dilation. Even on Earth, gravity affects the flow of time, albeit to a much smaller extent. Time passes slightly faster at higher altitudes, where gravity is weaker. Astronauts on the International Space Station, for example, age a tiny bit slower than people on Earth. This difference is minuscule, but measurable. It demonstrates that time is not absolute, but rather a fluid concept influenced by gravity. GPS and relativity keeping time with Einstein's universe. The Global Positioning System, or GPS, relies on a network of satellites orbiting Earth. These satellites carry atomic clocks that keep incredibly precise time. However, because the satellites are in a weaker gravitational field than Earth, their clocks run slightly faster. To compensate for this time discrepancy, GPS satellites are equipped with relativistic corrections. These corrections ensure that the GPS system provides accurate location data. It's a testament to the practical applications of Einstein's theories. A universe of perspectives, relativity, and our place in the cosmos. Einstein's theory of relativity has profound implications for our understanding of the universe. It revolutionized the way we think about space, time, and gravity. Before Einstein, we believed that time was a constant, ticking away uniformly for everyone, everywhere. But relativity tells us that time is flexible and can be stretched or compressed depending on various factors. It tells us that there is no single universal now. Instead, each observer has their own unique experience of time. This means that two events that appear simultaneous to one person might not be simultaneous to another. This concept is known as the relativity of simultaneity. Time is relative depending on your frame of reference. For instance, an astronaut traveling at a high speed in space will experience time more slowly compared to someone on Earth. This phenomenon is called time dilation and has been confirmed by numerous experiments. What one observer perceives as the present, another might perceive as the past or future. This is because the speed of light is finite, and it takes time for light to travel from one place to another. Therefore, our perception of events is always influenced by the time it takes for light to reach us. This concept challenges our intuitive notions of time and space. Black holes, for example, are regions of space where gravity is so strong that not even light can escape. They warp space and time to such an extent that time itself seems to stand still at their event horizons. It suggests that the universe is far more complex and interconnected than we once imagined. The fabric of space-time is a dynamic entity, constantly being shaped and reshaped by the mass and energy it contains. This interconnectedness means that changes in one part of the universe can have ripple effects throughout the cosmos. It also raises intriguing questions about the nature of reality itself. If time and space are not absolute, then what is the true nature of the universe? Are there other dimensions or parallel realities that we have yet to discover? These questions continue to inspire scientists and philosophers alike, pushing the boundaries of our knowledge and imagination. Beyond the horizon, unraveling the mysteries of space-time. Scientists continue to explore the mysteries of space-time. They are searching for answers to some of the biggest questions in physics, such as the nature of dark matter and dark energy, which make up the vast majority of the universe. Understanding space-time is crucial to unlocking these secrets. By studying the behavior of objects in extreme gravitational fields, such as black holes and neutron stars, scientists hope to gain a deeper understanding of the fundamental laws of the universe. Time travel possibilities, fact or science fiction? The concept of time travel has captivated the human imagination for centuries. While time travel into the past remains firmly in the realm of science fiction, Einstein's theories do allow for the possibility of time dilation. However, even if we could find a way to travel through time, the paradoxes and ethical dilemmas it would raise are mind-boggling. It seems that time, like space, holds many secrets yet to be uncovered. Conclusion: space-time and the nature of reality. Space and time are not separate entities, but rather intertwined aspects of a single unified fabric. This concept, which may seem abstract and difficult to grasp, is fundamental to our understanding of the universe. Imagine space-time as a vast, flexible sheet where every object with mass creates a dent or a curve. This curvature is what we perceive as gravity. The more massive an object, the deeper the curve it creates, influencing the motion of other objects around it. This fabric, known as space-time, is shaped by gravity, and it in turn governs the motion of objects within it. For instance, planets orbit stars not because they are pulled by an invisible force, but because they are following the curved paths in the space-time fabric created by the star's mass. This elegant dance of celestial bodies is a direct consequence of the warping of space-time. Einstein's theory of relativity revolutionized our understanding of gravity and its profound effects on the flow of time. Before Einstein, gravity was thought to be a force between masses. However, his groundbreaking work showed that gravity is the result of the curvature of space-time. This insight not only changed the course of physics, but also provided a new lens through which we view the universe. From the time dilation experienced by astronauts, where time moves slightly slower for them compared to people on Earth, due to their high speeds and the weaker gravitational field, to the relativistic corrections required for GPS satellites, which must account for both the speed of the satellites and the difference in gravitational strength between their orbit and the Earth's surface. The warping of time by gravity is not just a theoretical concept, but a measurable phenomenon with real-world implications. Experiments have shown that clocks run at different rates depending on their position in a gravitational field, confirming the predictions of relativity. This has profound implications for our technology and our understanding of the universe. As we continue to explore the universe and unravel its mysteries, we are constantly reminded of the intricate and beautiful tapestry that is space-time. Each discovery adds a new thread to this tapestry, enhancing our understanding and appreciation of the cosmos. Our understanding of space-time will undoubtedly continue to evolve, driven by the relentless pursuit of knowledge and the innovative spirit of scientists around the world. As we develop new technologies and conduct more sophisticated experiments, we will uncover deeper insights into the nature of reality, challenging our perceptions of reality and revealing the awe-inspiring wonders of the cosmos. The journey to understand space-time is far from over, and each step forward brings us closer to comprehending the true nature of the universe we inhabit.